Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to be modeling a parametric part from a detailed drawing. Now, this is a request that I get all the time, and honestly, I don't put a ton of stock or value in this process because honestly, in reality, the amount of times you have to model something from a detailed drawing is generally going to be slim. But a lot of people find good value in going through this process and understanding detailed drawings and how they relate to 3D models. So we're going to cover it in this video. The part in question actually comes from an old SolidWorks Certified Professional sample exam. Now I modeled it in Fusion and I created a detailed drawing, but if you've seen this before, it's likely because you took a CSWP sample exam probably many years ago. I don't know that they use this part anymore, but that's where the original part or the idea for it came from. In this video, what we're going to be doing is going through the process of creating parameters, or in this case, these variables that we're going to use to drive certain dimensions. This is a common thing you see when you're looking at modeling from a detailed drawing for an exam, for example, where they may change some of these values and ask you to update things like the mass properties or change the physical material that's used and measure the mass, and that's how they test whether or not you did it correctly. So we're going to follow that lead, that example, by using those variables or those values so we understand how to do that in Fusion. When we're going from a detailed drawing to a 3D model, there are going to be some different approaches that people take, but my approach is to try to look at primitive shapes and think about the order of operations in which things were built. So what I mean by that is, as we look at this part, it has a rectangular base that is a specific height, in this case 25 millimeters. So in general, we can start by defining that base shape, which is the value A by B. So A tall and B wide, and then it's a thickness of 25 millimeters. Other sections, for example, this little raised section with the counterbore hole, that has to come before this recess happens because that's completely offset from the profile that's made. Now, with that, we also need to think about how to define the whole location, what's the order of operations where we're going to add things like these cylindrical bosses on the top, because the center of them would have the rib, that raised section in the center. So we need to think about how we're going to add them to the model, at what point we're going to add them, and so on. So in this video, we're going to work through this entire process starting from scratch. If you go to the description of the video, you'll see a link to this drawing. So you can download the drawing and you can make sure that you have it open on a second screen. We are going to be referencing these dimensions, and I'll pull it back on the screen from time to time as we need it. Another thing to note is we just released a new desk mat in our merch store that has metric and standard tap and hole charts, and it's got some general information about bolts and threads and values for different types of loads that can be used on different bolts. So with that information, that mat, I got it yesterday. It's been actually pretty handy already. But if you're looking for a new desk mat and you do have to reference hole and tap sizes all the time, make sure that you take a look at the description of the video. I'll also put it on the screen here. You can find that in our merch store. So without further ado, let's go ahead and get started with a brand new document. So with the new document, we're going to make sure that we're using the metric unit system. Fusion's updated recently, or in March, to where we now have our unit system that includes mass. So we're going to be using millimeters and grams for mass. That's the standard. If you happen to have changed your default settings, then make sure that you do switch to metric. Otherwise, you're going to have to manually enter mm in all the dimension boxes, and it's just going to be a pain. The first step in this process, because we do have the parameters that we want to include, is to go ahead and open up a parameter dialog. So with this, we're going to have the ability to enter the A, the B, the C, and so on. And the way this works in Fusion is we can't actually just enter A. It won't accept that as a valid name. So what I'm going to do is I'm going to start with VAL for value, A, and I'm going to tab over to the enter expression and enter the value of 213 millimeters. We hit enter, we do this again, VAL B, tab over until we get to the expression, 200 millimeters for B, and so on. Now, I do wish that there was a quicker way to keep this dialog open or treat it more like a spreadsheet, but we do have to click that plus button every time, unfortunately. So value C, this is going to be 170 millimeters. Value D, tab over, this is going to be 130 millimeters. value E, this is going to be 41 millimeters. Value F, I'm not going to include here because those values we're going to enter in our whole dialog. You could certainly enter them here and link them, but honestly, it's just going to be easier to do it in the whole dialog directly. So then we've got value X. This is going to be an equation including value A and divided by 3. So it gives us a value of 71. Next, we've got value Y, and this is going to be value B divided by 3, space plus 10. Now everything's going to be in millimeters because that's the unit in here, so we're going to say okay. And now we've got variables or values for A, B, C, D, and E. F we're going to do directly in the whole dialog, and X and Y. If you do hear some noise in the background, I do have a 3D printer that's pretty much running constantly right now for the GPZ build series tail section. So unfortunately, I just need to keep it running. So hopefully it's not too loud on this video. Now that we've got everything set, we want to go ahead and start our first sketch on the top plane. We need to pay close attention to the orientation of X and Y because we're not dealing with a square. We're going to start with a rectangle and make sure that we set the rectangle to be from the origin. Anytime you're modeling, you want to use the origin and symmetry whenever possible. This part is not going to have symmetry, but starting at the origin is generally accepted as the way to start most models. Now, if you happen to start at 0, 0 and move up into the positive values, that's fine as well if that's how you like to work, but I strongly suggest getting used to using the origin. So for our width value, this is going to be value B. So you can start to type this in. You don't have to worry about caps. And then we're going to hit enter. Then we're going to hit tab to go over to the other one. And this is going to be value A. And I have the option turned off that automatically scales based on my first dimension. That is in the user preferences. Now, I found that this was actually kind of annoying because every time I would enter a dimension on a design, it would zoom out on the entire thing. And I just found it to be more annoying than anything, so I turned it off. But yours is likely, if it's all the default settings, yours is likely going to zoom to fit based on that first dimension. Now, at this point, we also need to make an important note about things like a fillet radius that's used on a solid part. Now, in most cases, you want to add those fillets as a feature for a couple different reasons. The calculation is going to be different when you have the fillet in a sketch versus as a feature, but the benefit is it's much easier for us to deal with changing that fillet as a feature after the fact than coming back into the sketch and dealing with it there. In most cases, when you have to go back to a sketch to edit a fillet, you run a higher risk of it breaking a sketch. So for example, the center point rectangle, if we add a fillet to the corner, we are going to get a warning about constraints that are being removed because these edges here, these construction lines, are no longer hitting the intersection of those outside edges. So in general, Fusion has been pretty good about fixing those and applying new constraints, but I prefer to do things at the feature level when possible. The next thing that we want to do is we want to extrude this up a distance of 25 millimeters. That's a value that we see on the detailed drawing. And then I'm going to go ahead and add my fillet. This is going to be to all the vertical edges. And looking at our detailed drawing, that fillet radius value is going to be 10, and then we're going to hit enter. Now, at this stage in the design, we really need to think about what comes next for the overall design. Now, there are two main features that I think come next. One is going to be the wall, the 15 millimeter thick wall, and two is going to be that small pad in the bottom right-hand corner that has the counterbore hole. Now, for me, I prefer to add the wall first, but really there's no good reason. It's just my own personal preference. So I'm going to start a sketch on this top face. We're going to right click, create a sketch, and I'm going to begin just adding the general line. So from here, we'll come up, right click, and click on the green check mark, and then we'll come and get an arc, and we'll go between these two, and then right click and say okay. Now at this point, we need to add some constraints. If for some reason you didn't get either a perpendicular or a persistent constraint for vertical or horizontal, make sure that you do have those lines be vertical or horizontal. Next, Because the dimensions on the detailed drawing have this line and this line both at 80 millimeters, I'm going to make them equal. And the last thing that we want to do here before we add dimensions is use horizontal vertical. The center point of the arc is shown at the extension lines of both of these edges. So we're going to take that center point and this end point of our line and make them horizontal. And then we'll do the same thing for the vertical one, and that should lock that part in. Next, we want to add a dimension. Now, from the bottom edge, as we're looking at it, to this edge here, this is going to be value C. So VALC, and hit enter. Because everything is currently defined, these are equal, we're pretty close to having that section fully defined. We're going to come down here. It's going to be a driven dimension. And you can see that it's listed at 170. So those are okay. The width of this should be 80 millimeters based on the detailed drawing. And if you want to add a driven dimension just to validate, you can see that side is 80 millimeters as well. The next step is to offset this. So we're going to take the entire chain and offset it 15 millimeters. One thing that we need to be careful with in Fusion is with the offset, notice that this point is floating. We want to make sure that it does fill in and turn black so that it's snapped to those edges. We'll have a profile either way because this is a horizontal line or it's perpendicular to this edge. And that means that point by default will just be on the edge. But without that constraint, we run the risk of accidentally moving it. And if we had moved it inward, we would lose that profile. So now we're going to finish the sketch. The profile selected so we can extrude it. Now here's where we want to be careful. With our dimensions on the detailed drawing, we have a dimension from the bottom of our part, a total height of 95 millimeters. So if we want to do some math, we could remove the 25 height of the base, but I like to go to my the start from object, start here, and go a distance of 95 millimeters, and make sure that they join together. Now, the reason I prefer this is, again, I'm using the referenced dimension on the detailed drawing. I don't have to worry about doing some calculations because we didn't have a variable set for the 25 millimeter height of that base. That means that I would have to manually enter it. And if I had to go back and make changes, it could cause problems. But I know because the detailed drawing references the height of this based on the bottom of the part, if I define it in that way and any changes are made, it's very easy for me to find and change that dimension because I know it's 95 millimeters. I don't have to say, okay, well, it's actually 70 millimeters, or if something changed, it's 60 now, and we have to go find that. The next step in the process, again, is to either create that little pad that's in this corner or to start to add those cylindrical sections. Now, again, it doesn't really matter which one you do first, but because I built this rib wall here, I'm going to start by adding those cylindrical sections. Now, the way that I'm going to do this is as a solid, and I'll come back in a secondary sketch and remove the inside. And the main reason for that is because the vertical rib that we created is going to potentially cause a problem with this. Now, we have to remember as we're looking at this, on the detailed drawing, that bottom left view, the outside diameter here is value X. So we need to make sure that we are referencing the correct value. The height of that is based on the height of that wall at 95 millimeters, and the center of the hole is 7.5 millimeters off of this wall. So that's half of the distance of that 15 millimeter wall. So that's why I could go ahead and just use a midpoint relationship here. It's something to keep in mind that 7.5 millimeters is half of the wall, but it's not dimensioned in that way. If you were going off of an exam, you would want to pay close attention to make sure that that was the case. If you didn't want to use this midpoint relationship, all we really need to do, let's go ahead and just move this out of the way. All we really need to do is add a dimension that is 7.5 millimeters from the side, and then make sure that this point is coincident with the top. That would lock it in. So again, you have to think about these things when you're trying to model something from a detailed drawing. Do you want to use those exact references, or are you going to take basically some liberties with the design intent behind it? So what we're going to do now is select extrude, grab both of these profiles. But if we look at the detailed drawing, this doesn't start from this face. It's actually 10 millimeters off. What we could do is use two sides and extrude it 10 millimeters one way and then the full distance the other way, which is in this case distance D. But because distance D it wouldn't be able to take into account that 10 millimeters, the best option for us is to offset this 10 millimeters. So basically we're taking our sketch plane and moving it 10 millimeters. And then the distance we're going to go is in the other direction minus value D. We need to make sure that we join these together and we say okay. Now, if you want to verify this, we can go and just double check the overall distance. Make sure that it is 130 millimeters. That's value D in our chart. If you happen to try to do two directions, you need to remember that it's D minus that 10 millimeters because you have to account for that offset. So that's the cylindrical section on one side. We'll repeat the process over here. Again, I'm going to use the circle tool, which is C on the keyboard. The diameter in this case is going to be value Y. So this one is slightly larger. And once again, if we look at the detailed drawing, it's offset 10 millimeters. So we're going to go 10 millimeters in this direction and then minus value D and hit enter. Then make sure that we join them together. And once again, the reason we're not using the inside diameter in this case is because it would complicate the process because that rib came all the way up to the center. So we couldn't just simply extrude the outside and inside diameter. We would then have to go and remove those sections on the inside. So from my personal preference, it's much easier to add this as a solid and then remove that extra material later. Now let's go ahead and take care of those holes. So another sketch on this side, C for a circle. This is going to be value E. Hit enter, finish the sketch. We're going to extrude that. In this case, I'll start to pull it in the negative direction and then just say all the way through. And then we'll repeat that process over here. So create sketch, C for circle, value E, and then we'll extrude it. So E on the keyboard, through all, and say okay. Now, using things like through all, starting from an object or going to an object are extremely important when we're modeling things parametrically, because that means if we happen to change the value of D, we don't have to worry about that extrude distance not being far enough because it'll always go through the model. I'm going to deal with the chamfers now just because we're working on these features and I don't want to forget them. So I'm going to grab all of these inside edges and then have a 2 millimeter chamfer based on the note on the detailed drawing. It says 4 times 2 times 45 degrees. Since we're doing equal distance, that means it's 45 degrees. You could also do distance and angle. You can manually set it to 45 degrees if you were worried about that being accurate. So now we've taken care of those cylindrical sections. Really what we need to do is add that raised section, and then we need to add the recess. So we're going to start a sketch. We're going to use our line tool, which is L on the keyboard. We're going to come up and over, and then we're going to give them dimensions. So D on the keyboard. Now this has a manual dimension. We didn't have a parameter for it. It's going to be 60 millimeters in this direction and 60 millimeters in this direction. We need to think about whether or not we want to include that fillet here. So this can be done again at the sketch level. It's going to be a 15 millimeter radius. We could also do it at the feature level after we extrude. In this case, it's honestly not going to make too much of a difference. The point where it would make a difference, and I'll actually do Control Z to undo, the hole that's going to be in the center that we're going to use the hole wizard for, the point where this would make a difference is if we wanted that to be based on a midpoint relationship like this. So if we were going to turn these into construction lines, the midpoint relationship only works because the dimension on the detailed drawing is 30 millimeters to this point and 60 millimeters for the overall width. So for example, if I dimension this and create a driven dimension, that works because of we didn't modify that line. If I happen to add a 15 millimeter radius fillet here, this is no longer the midpoint, which means that if I were to snap this to the midpoint, that's no longer 30 millimeters. That doesn't put the hole in the right location. So again, these decisions come down to how you approach the model, whether or not you're using things like a midpoint relation and adding this fillet as a feature after the fact, Or if you happen to decide to add it as a sketch level, we need to come back and add that center point location after the fact. Now, the reason I'm doing it this way is because the point on this sketch wouldn't work for our hole feature anyways. And that's because the hole feature is going to start from 10 millimeters above the sketch plane, and there's not really a great way to snap to it, so we have to create another sketch anyways. But we're going to take this, we're going to extrude it up. We could simply say 10 millimeters because we know the base is 25 tall and this section is 35 tall. But again, I think it's a good idea to start from the bottom and go up a total distance of 35 and join them together. And again, because we're using that 35 millimeters based on the detailed drawing, even though we didn't create a parameter for this, we can go into all the features that we've created and we can find that 35 millimeter dimension, and it'd be easy for us to reference. Also note that you can right click and rename features. So we can call this a raised pad, for example. And then if we go into modify parameters and we look down here, the feature is called raised pad, and it's easier for us to find. So again, it kind of depends on the process that you're going through and what you have available to you before you model something. I'm going to go ahead and start a new sketch on this pad. I'm going to use a sketch point because this is going to help us find the location of that hole. And then we're going to use our dimensions. So D on the keyboard, 30 millimeters, and then 30 millimeters here. Now, it can be very easy for us to make things equal, like clicking on this dimension so that they're always the same. We do need to remember that if we're asked to update these dimensions, for example, if this pad changed from 60 by 60 to 70 by 60, and these were no longer 30 by 30, it was 35 by 30, then we need to remember that these are linked and have to come back and fix them. You really don't know that information because when things are modeled, we can use midpoint relations, we can use symmetry, but when you have a detailed drawing and you measure the distance of that hole from the edge, you don't really know these factors. So now we're going to add a hole. We're going to select that face and that point. We're going to use a counterbore with a simple hole. We're going to make sure that it goes through all. And we're going to set the counterbore diameter to 30 millimeters, a distance down of 10 millimeters, and we have a passing hole of 15 millimeters. Now, if you are familiar or if you found the original Certified SOLIDWORKS Professional sample, there was actually an error on it. Because it lists it as an M8 close fit hole. And if you have one of the new lead desk mats with the tap chart on it, you'll know that an M8 passing or a close fit hole is 8.4 millimeters, but they also list the diameters as 30 and 10 and 15 for these values, which isn't realistic for an M8. It would be 8.4 for the diameter, and it would be about 18 for the counterbore head and so on. So again, this is why I didn't really put these values in the variables because we could come in here and change them, but you certainly could link to those by simply typing in whatever the name of your parameter is. For our purposes, I'm just going to go ahead and manually enter them. The last thing that we really need to do here is we need to deal with this recess. And now that we've got all the other features created, all we have to do is create a sketch here, go to offset, and offset that in a distance of 9 millimeters. Keep in mind that if we decide to add a fillet here, we are going to break some of the offset. This is just an inherent problem that happens. What'll happen is if we add fillets to each of these sides, we no longer have an offset between those two edges. So it's my suggestion for something like this to add the fillets as a feature after the fact instead of at the sketch level. You certainly can, you could add them here, but I think it's better if we do them at the feature level for this example, so that way the sketch is still fully defined. That means if we change the overall size of our part, that 9 millimeter offset will still be true. So now we'll select that, we'll extrude it down. And again, if we look at the detailed drawing, we have a dimension of 5 millimeters from the bottom. So the way that we're going to do this is say to object, and we're going to put an offset of minus 5 millimeters. Once again, it's important that when we're dimensioning a part like this, if we're using a detailed drawing, that we try to dimension it based on the detailed drawing. So instead of saying go down 20 millimeters, leaving 5 at the base, we can extrude it all the way to the base, leaving a 5 millimeter thickness on the bottom. And again, the reason for this is if we happen to change any of these dimensions, we know that it'll update properly based on the detailed drawing. Next, we're going to add fillets to all of these vertical edges. And looking at the detailed drawing, let's go ahead and rotate this one around. Looking at the detailed drawing, there are going to be 10 millimeter radii here, and there's 6 of them. So 1, 2, I'm going to hold down Control so we can see it. 1, 2, 3, 4, 5, and 6. We'll say OK. Now, this should be everything. This should be all the features. And if you want to double check it, you can always go and do inspect section analysis. And for example, take a look at what it looks like here. Go down, make sure that this looks like it does on our detailed drawing. We can also do section views through that hole. Again, make sure that everything appears to be correct. One other thing that we should consider when we're thinking about modeling mechanical parts is going to be actually applying a physical material. This can be done at the body level or the component level. In our case, it would make sense, since we only have a single body, to apply it at the top level. A reason that you might apply it at the body level is because maybe you've got multiple bodies in a design, you're not using components, and you want each one to have a different type of material. So at the top of our browser, we haven't saved this yet, which is not a good thing, but we're going to right click. We're going to select physical material. Now inside of here, you can navigate through your library. We'll go to the Fusion Material Library. We'll pick metal. We can pick any type of metal that we want to use. I'm going to go ahead and go down to a steel material. Let's see. We want an alloy steel material. Let's keep going. All right. So when we have this, we can drag this on the material that's in the design. We can drag it on the body on the screen. We can drag it on the body in the browser. Or we can drag it on the component in the browser. Any of those options will be fine. And then to validate this, we can right-click on the component and go to Properties, and it'll tell us what material is applied here. So when we do this, you can see the physical material. It gives us our mass. This is 14,263. Gives us our volume, our density. Keep in mind that these numbers are rounded. And then as we go down, you can see the alloy steel is our material. We can go to a bounding box. We can find a moment of inertia, center of mass, and we can sort of work through all these different pieces of information. The properties for the component are going to be different than the properties for the body slightly. And what I mean by that is the component properties are where we put things like part number, part name, description. If we go to the body properties, we're not going to be able to put part number, part name, description. We're going to just get the physical properties of the body. There are also other things that we can do, like inspect and measure. We can also turn on the center of mass for this body, and it'll display a little glyph where the center of mass is, which is not at the center of the part, just because we've got more mass with these 2 cylinders here. And that's going to show up in the analysis folder. So there are lots of little things that we can do here. If you happen to have a material that doesn't match something inside of the material library, you can go to your Utilities tab and go to your material library. Now inside of here, you would navigate to the Fusion materials. Let's say metal. Let's say that I wanted 3003 aluminum. I could right click and add this to my favorites. And then I could go to my favorites and find that 3003 aluminum, and I can edit this. I'm going to go ahead and expand this a bit. So for example, let's say that you had an aluminum material, but the density wasn't correct. Then you can come in here and you can modify the density value to make sure that it matches a physical material that you have. And then if you are going to apply that physical material, let's say at the component or the body level, then all you need to do is in the material browser, go to your favorites and find the aluminum 3003 that you added. So let's say here, drag it to the body, drag it to the component, or drag it over the steel material that was applied in this design to override everything. And then once again, we can go to our properties. We can see that we should have the aluminum 3003O that's been added. We can see the mass is now different. The volume should be the same. The volume in the area should be the same, but the density and the mass obviously will change based on that material. So that's the basic process. I know there are a lot of different decisions that happen along the way, things that we need to decide when we're modeling either from a detailed drawing or from basically from scratch if we're making our own designs. But thinking about the order of operations is always important. When you have a design, and in this case we had a detailed drawing, we could start with a basic shape like this rectangle. We could go through the process of making those design decisions as we built it up step by step. Some designs will be easier than others, of course, because we can just make a single profile and revolve it, or we can stack a couple of simple shapes together. But taking a methodical approach and trying to break down a design into some basic shapes or basic parts is going to be a universal skill that can apply to pretty much anything that you're doing. One good thing that we can do after the fact, and I'm going to go ahead and save this before I try this. So we'll call this param model. I'm going to go into my change parameters and we'll drag it over here. We'll bring the body up here and we'll make some changes. So 213, let's make this 250, the design updates. Now keep in mind that the location of these cylinders is driven off of 80 millimeters. It's not driven off of, or it's driven off of another parameter C. So let's say 200, it's going to move that value up. This is going to change the recess that we have. It's going to change this arc that we have, but the model is updating. Now let's say that this 200, we actually want to make 190. There might be a case where the model fails based on other geometry, but keep in mind that we are able to make these changes by going into our change parameters and modifying these values. So whenever you have a model like this where you have a potential problem, so you can see here, we have a potential problem with updates, we just have to go back and think, okay, well, what is the extent, what is the amount that we can actually make changes to this model? And at what point are we going to exceed the ability to update the model? So there are dimensions in this case from our detailed drawing that are controlled by these parameters. So A, B, C, D, and so on. But other values, like this 80 millimeters, for example, that is manually entered, which means that it's not going to update if we change the overall size of this. So if we make this thing narrower than that piece can fit in there, then it's not going to update properly. But in many cases, when you're creating models, it's going to be sort of a one and done. Most people aren't creating models like this that need to parametrically update. But if you are, those are things that we should think about. Now, if you have any questions on this or want to see more videos like this where we're taking a look at a complex or semi-complex part and walking through the process of modeling it, please let me know. And again, thanks for watching, and we'll see you in the next one.